Hello, good evening and welcome to the Mathematics News. This afternoon we are going to be studying more friction. More friction. Yep, you guessed it, more friction. And this exercise 8a that we've been working through takes a long time. I mean, a really long time. It took me ages. I've just finished exercise 8a completely. I've done questions 23, all of them take some time, but they get easier. They get easier. The exam questions at the end definitely are easier than the ones at the beginning. By the time you get that far, you're an expert. Absolutely brilliant. What I want to highlight is two things. One of them is that sometimes the mass is not important. There's going to be more detail of that coming up soon in this report. But the mass of the object can be big or small. It doesn't always matter if you don't know it. You know, you can work out what's going on, you can find the acceleration. I also want you to know that this takes practice. And if you go every single question, if you complete every single question, you will get the hang of this. There are about, 5 or 6 exam questions at the end. And if you get that far, you'll feel like you understand it, which is what I want you to do. So through this lesson, I want you to carry on. I want you to ask me questions. If you get stuck, you can check with me. Tomorrow morning as well, we have a double lesson. I think there should be enough time to get all the way through the questions. If you manage to get all the way through the questions, earlier than that, that'd be amazing. But I think we should spend some time. Next week, we're going to move on to chapter 9. And in chapter 9, there is stuff involving work, energy, and power. And that's worth us starting afresh. I think on Monday, we're going to introduce those concepts. And then we'll practice all the way through chapter 9 next week. But let's carry on with chapter 8 this week. And finally, what I really want to know, what is really driving me crazy, is who is putting all these little boxes on top of slopes and then working out the forces involved. Why? I want to just quickly mention some questions that don't give you the value of theta, but it's hiding in there somewhere. For example, they might tell you something like this. There's something on a slope. Who put it there? Nobody knows. But there is the tan of the angle is 6/8. So if they tell you this, you can work out everything you need to know. I mean, you could work out the angle, but it's actually easier to think of this as being the opposite over the adjacent. That means that this one here is the 6 and this one is the 8. And then you can use Pythagoras to work out what this one is. The hypotenuse is going to be the square root of 36 plus 64, which makes that 10. And that means from there, you can say the sine of the angle is the opposite over the hypotenuse, and the cosine of the angle is the adjacent over the hypotenuse. So you can then use those, especially if you're breaking down the forces of the weight. You need to know this horizontal one and this vertical one, and you can use sine theta and cosine theta like that. Sometimes, and this is in one sneaky question in exercise 8a, you're given, hidden in the question, this distance here. They tell you, say for example, this is, 400 meters, and they tell you this distance here is, let's say this is 120 meters. This just happens to be casually dropped in there, and maybe you're thinking, oh, I'll need that later on when I'm using SUBAT. But actually, it's there because it can help you work out the size of that angle. Because you need this angle, you need the cosine of this angle, you need the sine of this angle, because you might have to break down the components of the weight again. So if you know two sides of the triangle, you can work out an expression for the angle. This one means that the sine of the angle is 120 over 400. And from there, you could work out the cosine of the angle, which would be the square root of 1 minus 120 over 400 squared, using sine squared plus cosine squared is equal to 1. So even if you're not told the angle, you might have some information that tells you what the angle is. Sometimes the mass of the object you're dealing with is not important. And this is quite surprising, but it's something that crops up in the occasional question. Not every question, but sometimes you're not told the value of the mass of an object that's moving or in equilibrium, but you can just call it m. So if you're not told and you need to put it into a formula, just call it m. Sometimes the m cancels out. I just want to show you a quick example of this because it's something that's worth considering. Imagine there is a box on a slope. Somebody's put a box on a slope and the box is about to sort of slide down there. Well, we're not told the weight of it, but let's just call it m for the mass, right? That means that the weight of it is going to be m times the acceleration due to gravity. So that's mg or 10m. Okay, so that's the force of the weight of a box with m kilograms. And this is going to slide down the slope and there's going to be some friction. Let's say this is a situation where there is a rough surface here, so we're going to have some friction. There's a normal reaction force up here. There's no forces pulling it down, but it's going to start to slide down because the weight of the box is going to make it sort of slide down. Okay, if I want to break this down into the components, I have a right angle here. This one is adjacent to that angle. By the way, that's a right angle here, 30, that's 60, that one is 30. In all of these sorts of situations, you end up with this angle here is the same as this angle here, if you draw that right angle triangle. So this force going this way is going to be 10m cosine 30. That's the one going straight down. The one that's sort of going horizontally, well, it's sort of parallel to the slope. That one is going to be 10m sine 30, because that one is going opposite that angle of 30, so it's going horizontally. And we can forget about that now because we've broken it down into the components. And if I wanted to know what was happening, I would use F equals ma. All the forces combined here, I've got this one, take away the friction. So that's 10m sine 30. Take away the friction is equal to the mass times the acceleration. We know now that there is a formula that connects together the normal reaction force, this one, and the friction. And this is using the coefficient of friction that we talked about previously. And the formula is friction is equal to mu times r, where mu is the coefficient of friction, and that's usually somewhere between 0 and 1. It can be a little bit higher than 1, but it's basically a very small number. It can't be negative, by the way. Otherwise, that means the box would be going up by itself. That'd be weird. So it's 0 to 1, roughly. Here, we needed an expression for the friction. We know the coefficient of friction is 0.3. The normal reaction force is the same as that component going down there because it's not going off into the air, it's not going through the slope. So the friction is equal to 0.3 times that one, 10m times cosine 30, run out of space there, that's times. So this equation down here becomes 10m sine 30 minus, that's going to be 3m cos 30 equals the mass times the acceleration. We don't know the mass, but the mass has appeared everywhere now. It's appeared here, here, and here, so it cancels. And from this, we can work out the acceleration by doing this times this, take away this times this, and the acceleration will come out to be a relatively nice number. 10 sine 30, sine 30 is a half, so that's 5. 3 cos 30, it's not a nice number. 3 cos 30 is about 2.60, and that equals the acceleration. So in this case, the acceleration is going to be 5 minus 2.6, which is about 2.4 meters per second. And that's a surprising fact. It's the mass doesn't make any difference. And this relates to that famous experiment where an astronaut dropped a hammer and a feather on the moon. If you don't take into account the air resistance, then the mass doesn't make any difference. This could be a heavy object or a light object, or it could be a small object or a big object. When it slides down the slope, it will have the same acceleration. If you're ignoring air resistance, which we are doing, then the mass makes no difference. It cancels out in this calculation. And that's quite a beautiful thing. It's sort of counterintuitive, but you guys can appreciate that. It's amazing.